Hello everyone. Today we are going to have an interesting topic as diagonalization of a matrix of order 3 by 3 with arithmetic and geometric multiplicity. In the previous video we have learned this diagonalization process for 2 by 2 matrix. Now the continuation of this video has been done here. இல்ல இதுக்கப்புறம் record பண்ண ஷேர். Hello everyone. Today we are going to have another interesting topic, that is the continuation of my previous video. This is the diagonalization of a matrix of order 3 by 3 with arithmetic and geometric multiplicity. In the previous video I have explained this diagonalization process for the matrix of order 2 by 2, and if you want to know that, the link has been given in the description. You can make use of it. Now let us move on to this matrix of order 3 by 3. So before moving on to this, let us have a short recall about these basic definitions. A matrix A is said to be diagonalizable if we can able to find the invertible matrix P such that it should be satisfy this expression called D equal to PAP inverse, where P is the columns of the eigenvectors of the matrix A, and D is the diagonal matrix whose the diagonal entries should be the eigenvalues of the given matrix A. And arithmetic multiplicity is, it is how many times the root, or we can call the root as eigenvalue. So how many times the eigenvalue appears in the characteristic equation. The geometric multiplicity is the number of independent eigenvectors that have been arrived for each eigenvalue. The another version of finding this geometric multiplicity is dimension of kernel of A minus lambda I. And the relationship between the geometric and arithmetic multiplicity is always the geometric multiplicity should be greater than or equal to 1, and this geometric multiplicity should be less than or equal to arithmetic multiplicity. So if this arithmetic and geometric multiplicity is equal for each and every eigenvalue for the given matrix A, then we can able to say the matrix is diagonalizable. Now this is the methodology that we have to use to find the diagonalization of a matrix. So first we have to find the eigenvalues of the matrix A with the help of A minus lambda I, and next we want to find the eigenvectors. Here I have explained two methodology, cross multiply and null space method. And after doing these two steps, we have to check the arithmetic and geometric multiplicity for each and every eigenvalue. So once these three steps are done, then we can say the matrix is diagonalizable. Then we can further move on to the steps 4, 5 and 6. Or else we have to stop and we have to say that the matrix is not diagonalizable. So after checking these three steps, once if this arithmetic and geometric multiplicity is equal, then we can find the matrix P with the help of eigenvectors of the eigenvalues. Then compute P inverse, then you can check this expression is satisfied or not. Now let us have a matrix of order 3 by 3, where this is a symmetric matrix of the structure A, B, 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 A, B, 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 A. So in this case, if your matrix is of this type, then the direct formula where we can use is for the characteristic polynomial. You can write the expression as A minus B to the power n minus 1 into A plus n minus 1 into B, where this 3 is nothing but it is the dimension of the given matrix. And from this, you can directly able to find the eigenvalues using the formula A minus B, A minus B and A plus 2B. Let us have this in detail in the upcoming problem. So let us take this matrix of order 3 by 3, where the entries are 3, 1, 1, 1, 3, 1, 1, 1, 3. So based upon the previous structure, here the value of A is 3 and the value of B is 1. So directly I can able to find the eigenvalue. So the eigenvalue formula is A minus B, A minus B, A plus 2B. So according to this, the eigenvalues are 2, 2 and 5. So from this you can find out that the eigenvalue 2 comes for 2 times and the eigenvalue 5 comes for 1 time. So the arithmetic multiplicity of the eigenvalue 2 is 2 and the arithmetic multiplicity of the eigenvalue 5 is 1. Now let us have, this is nothing but some important properties that the matrix has to be followed. So the trace of the matrix In this problem, the trace of the matrix is 3. So every trace of the matrix should be equal to the sum of the eigenvalues. So according to this problem, the eigenvalues are 2, 2 and 5. So the sum is equal to 9. So the first trace property has been checked. Now the determinant of this matrix should be equal to the product of the eigenvalues. So here the product of the eigenvalues is 2 into 2 into 5, that is 20. So you can able to find the determinant of the matrix, it is nothing but 20. So you can able to check of your own. Now let us move on to the first step to find the eigenvalues. So based on the methodology, determinant of A minus lambda I. So shifting to that structure, so the A minus lambda I has been come as 3 minus lambda, 1, 1, 1, 3 minus lambda, 1, 1, 1, 3 minus lambda. So after finding the determinant of this matrix and making the further simplification, the reduced expression which I have got is this lambda cube minus 9 lambda square plus 24 lambda minus 20 equal to 0. Now I have to reduce this cubic equation to linear factors. The shortcut trick I can able to find the factor is what are all the numbers I have got in the constant number. I want to find the factors of that number. Say for example, here at the constant number is minus 20. I want to find the factors that divide minus 20. So the numbers are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 5 and plus or minus 20. So you have to check that you have to substitute these values in the previous equation. Suppose let us say for example, here let us take plus 1. If I substitute plus 1 in this equation, if I get the answer is 0, then for this equation 1 is a factor. So by continuing that procedure, I have tested the value 2. If I substitute the value 2 in this equation, I am getting equal to 0. So from this I can able to find that the cubic equation have the root, have one root as 2. No, by synthetic division with the help of this factor lambda minus 2, I can able to find the quadratic equation lambda square minus 7 lambda plus 10. So from this quadratic equation, I can able to find the linear factors lambda minus 5 and lambda minus 2. So from this characteristic equation, the roots are 2, 2 and 5, which means I can able to say here the 2 comes for 2 times. So the arithmetic multiplicity is 2 and for the eigenvalue 5, the arithmetic multiplicity is 1. Now let us find the eigenvectors. So for the eigenvalue 5, I have to consider the structure A minus 5i into V. V is nothing but the eigenvectors x, y and z. So I have to consider A minus 5i. So in that matrix, in the diagonal numbers, you should subtract minus 5. So I am getting this matrix. Now I am just considering the vector and just I want to multiply it and equate it to 0. So from this, if I multiply minus 2 into x plus 1 into y plus 1 into z equal to 0. Likewise, you have to multiply each row and this column vector, you will be getting 3 equations. Now I want to consider one method, cross multiplication method, to find out the eigenvectors. The formula to find the eigenvector using the cross multiplication method is, here I have to consider only 2 equations. So I am considering only the first 2 equations. So here my A1 is minus 2, B1 is 1, C1 is 1. A1 is 1, B1 is minus 2 and C1 is 1. So based on that, I have taken the coefficients and this is the formula to find the eigenvector. So just substitute the values of B1, C1, B2, C2, C1, A1, C2, A2, A1, B1, A2, B2 from these 2 vectors and take a determinant of those numbers. Here it is displayed here. So after you take the determinant, you will be getting the eigenvector as 3, 3, 3. So I told you the eigenvectors, if it has any scalar multiple, just remove it. So here the scalar multiple is 3. So after removing that, the eigenvector I am getting is 1, 1, 1. Now let us find out the eigenvector for the eigenvalue lambda equal to 2. So after writing A minus 2i, the matrix becomes 1, 1, 1. It is nothing but completely the entries are 1. So obviously here the rows are not independent. So here I have to consider only one equation. Since the rows of this matrix are linearly dependent, the eigenvectors are found using the null space method, because this cross multiplication method will not work for this matrix. So considering this null space method, we found two eigenvectors. Here, these eigenvectors are constructed based on the property called orthogonality. The matrix, symmetric matrix, should have the property that all the eigenvectors of the eigenvalue should satisfy the condition of orthogonality. Say for example, the product of these two vectors should be equal to 0, like 1 into 1 plus minus 1 into 1 plus 0 into minus 2, it should be equal to 0. And simultaneously, these two vectors should satisfy the given equation. So based on that, two eigenvectors have been derived. So for the eigenvalue 5, one eigenvector, and for the eigenvalue 2, two eigenvectors. Now let us find the geometric multiplicity using this rank nullity theorem. So for the given matrix, let us find the geometric multiplicity. Say let us take A equal to 5. So for this matrix, using the rank row reduction process, this matrix have been reduced of this form, where the rank of this matrix is 2 and the dimension of kernel is nothing but the number of 0 rows. So the dimension of the kernel of this matrix is 1. So the geometric multiplicity for the eigenvalue 5 is 1. And similarly, consider A minus 2i. Here all the rows are identical, so only one row is independent. So after doing the row reduction process, the rank of this matrix is 1, which means these two rows will be 0. So the number of completely 0 rows are 2. So the dimension of kernel of A minus 2i is 2. So the dimension of kernel of A minus 5 is 1, and dimension of kernel of A minus 2i is equal to 2. So since the geometric multiplicity and arithmetic multiplicity are equal, let us move on to the construction of the matrix P. This P is nothing but the collection of the eigenvectors of the given matrix. So from this, if I consider the expression called P into A into P inverse, finally it will be giving the answer called this diagonal matrix, where the diagonal entries are the eigenvalues of the given matrix. So let us take the matrix P and find P inverse, and using this we can check this process. It has to be done, and we can check this verification of your own. So for this problem, we can conclude that once the arithmetic and geometric multiplicity is equal for each and every eigenvalue, then the diagonalization process can be continued and this verification can be also done. Now let us consider another example. 310030003. So in the previous example, we have considered symmetric matrix. It is non-symmetrical matrix. So here, like the previous methodology, we have to find the characteristic equation, and we found that for this matrix the eigenvalue is 3 and the arithmetic multiplicity is 3. And now let us find the geometric multiplicity for this eigenvalue 3. So let us consider the expression A minus 3i. So once we find A minus 3i, it becomes 0, 1, 0, 0, 0, 0, 0, 0, 0. So if I multiply this matrix with x, y, z, finally I have only y equal to 0. I have only one equation, that is y equal to 0. Which means here I have two free variables, they are x and z. Which means the free variables are nothing but my geometric multiplicity. So the geometric multiplicity of the eigenvalue 3 is 2. Unfortunately, the arithmetic and geometric multiplicity for the eigenvalue 3 is not equal. So this matrix is not diagonalizable. So in this video, we have considered two examples where one is symmetric and another one is non-symmetric matrix, where we have learned how the diagonalization process have done. So this topic, diagonalization, plays a vital role in scoring good marks in set and net examination. I hope you all liked my video. Thank you.